So, welcome back to the mass balance series. We were looking at the ideal plug flow reactor and its mass balance. We were looking at steady state again and what I called the lecture reaction, where we turn unhappy students into happy students with a first order reaction. And we will do this in an ideal plug flow reactor. So the plug flow reactor will be this one here. We will have a volume flow in here. There will be an initial concentration of unhappy students in there. And of course we will have some outflow conditions. We will have some volume in here. Yeah, and of course we will also have the volume flow out here. We will use a special way of doing that. Yeah. We will not look at the mass balance of the whole reactor, which is a bit tedious to do so, because first we will be looking at a volume element in here. Yeah. So a cross section where the actual flow goes in and a flow comes out with some concentration of unhappy students here and a concentration of unhappy students changed by direction. And in order to describe that, we make this volume element here infinitesimally thin. So we say, okay, this is dV, yeah, delta volume, and this turns then our change of reaction to an infinitesimally small one, so we can describe that as being the initial reaction plus something else, and as we're looking at the reactants, this will be negative. So, then let's look at the mass balance. Again, we will need the four constituents: input, output, reaction, accumulation. So the input will be V dot times the concentration of unhappiness. The output will be also V, but this time we will look at the change one. So this is this outflow concentration here. Again, you can choose to make this rather generic. We say, okay, this is the reaction. So we could say, okay, there's a rate. And this will take place in this infinitesimally small volume element. So this will be dV. And as we have perfect mixing within this cross-section, accumulation will be 0. So, be more specific, we can forget about accumulation. And we put in our specific rate equation here, just for demonstration purposes, saying, okay, this will be K times the actual concentration of unhappy students in this volume element. Okay, same argument as goes again for the signs. So input will equal output reaction. This will be vanishing, yeah, but as we have to put it in negatively, we get a minus, we get a double minus, which ends up in a plus. Again, reasonable, because we will have this amount, and this together have to equal the amount here. Okay, we can do some mathematics on that, and as we have now to integrate from 0 to here, to the overall volume, that's the reason why we actually will need to separate the variables. So we will sort everything according to concentrations and to volume. First step for that is to divide everything by. volume flow, which leaves us here concentration-wise alone. We will have concentration separated here, plus, and we will have K unhappiness dV over V dot. Okay, and we can do two things. You notice here concentration is on one side, on the other hand side, so we can subtract the concentration minus concentration of unhappy students, which will effectively cancel out these two terms here, so we get a 0 here. We wipe this away if you want. A bit untidy here on the blackboard, which leaves us with these two, and then we only have to divide by the actual concentration. In order to get to the next step, where we have the concentration-wise here divided by the actual concentration. Yeah, assuming that this will not be 0, of course. And we will have another term which is K times dV over V dot. Okay, which equals 0. I can now rearrange. I will put this on the other side, flip everything around, which leaves me with something a little bit more pleasant. So we will have something where we have on the left side all the concentration related things, K is a constant, and we will have negative things. About the integration, so we will need to integrate this. K is a constant as mentioned, and we will integrate on the left hand side over volume starting from 0 here, and we will do this until we have reached the overall volume of the plug flow, V. On the left hand side we start at 0 with concentration 0, and we will do this until we reach the actual concentration. And as unsurprising for a first order reaction, and unsurprising for a first order reaction, we see this familiarly here. We see that this will be the natural logarithm of the ratio of the actual concentration divided by the initial concentration. On the right hand side we can see that we get V, or a volume, divided by volume flow, which, believe it or not, is our hydrodynamic residence time again. So we get on the left hand side this logarithm, and we get on the right hand side K times tau, which, surprise, surprise, is the Dunn-Kruger number again. Yes! We can rearrange that to something more familiar. We can say, okay, concentration, so it should be A, should have it. Concentration of unhappy students to concentration of unhappy students. Initially, actually, is the exponential function of e to the power of kt or Dampköhler number. Yeah, so this is either kT, let's put Dampköhler, just to confuse us a little bit. So this is again minus Dampköhler number here. And as you may know, I'm more interested in happy students. We get the ratio of happy students compared to the starting amount of unhappy students, and this will be 1 minus the exponential minus the Dampköhler number. So, same thing here, that's vice versa. So, to see also this process, also in the plug reactor, is governed by Dampköhler. Yeah, saying that the residual value here will get low the higher the Dampköhler number is, and that the amount of, or the ratio of happy students also depends on the Dampköhler number, that you have more happiness the higher the Dampköhler number is. Again, in our model, same conclusion as before. What do we need? Longer lectures and higher indoctrination frequency. Very conclusive. Thank you very much for your attention. Again, short afterthought. Even if this model is equally crude as the other one for the CSTR, so it's still lecture, I prefer actually this kind of lecture where you all are present in the beginning and stay to the end. And you will also see later on, if you compare these two solutions, that this is the more effective way if we can't alter K, which is in your hands basically, I guess, and we can not alter the residence time, yeah, then you can see that this kind of lecture mode will be more effective. So be with me to the comparison. Thank you as an afterthought.